Welcome to the Explainer. Today, we're jumping into a huge one, logistic regression. Now, I know the name might sound a little intimidating, but trust me, this is one of the most important, most powerful tools in all of machine learning. And it's actually the secret engine behind a ton of decisions that happen around you every single day.
Okay, so let's get right into it with a question your email has to figure out constantly. Is this message spam or is it not spam? That's it. It's a simple yes or no choice. And that right there is the perfect way to start thinking about what logistic regression does best.
And once you start looking, you'll see these binary, these yes or no questions everywhere. Businesses are dying to know if a customer is going to click buy. Doctors need to predict if a patient is at risk for a disease. And of course, sports analysts are always trying to figure out if a team is going to win. Our world is just filled with these critical coin flip questions. And logistic regression, it was literally built to help answer them.
But, to really get why logistic regression is so cool, we have to first talk about why a much simpler tool, something we're all familiar with, a basic straight line, totally falls apart when you try to use it for these kinds of problems.
So a lot of the time in statistics, we start with what's called linear regression. It's fantastic for predicting things on a sliding scale, right? Like, what's the price of this house? Or what score will a student get on a test from 0 to 100? You just draw the best fitting straight line through the data. But what happens when the thing you're predicting isn't a number on the scale? What if it's just a choice, pass or fail, yes or no, a 1 or 0?
Well, here's the big problem. A straight line just keeps going. It doesn't have any boundaries. So if you keep extending it, it might predict that you have a 150% chance of passing an exam. Or even crazier, a negative 20% chance. And that's just, it's complete nonsense, right? Probabilities have to live between 0 and 1, or 0% and 100%. So it's pretty clear that a straight line is just the wrong tool for this job.
So if a straight line doesn't work, what's the fix? Well, the solution is actually really elegant. It's a surprisingly simple and very, very smart curve.
And here it is. This is the secret weapon of logistic regression. It's called the logistic function. You'll often hear it called a sigmoid curve, really just because it has this distinct S shape. Its whole job, its entire purpose in life, is to take any number you throw at it, positive, negative, huge, tiny, whatever, and gently squeeze it into a value that is always, always between 0 and 1. So you can think of this S-curve as a kind of universal probability converter. And that's its magic trick. No matter what the input is, the beautiful shape of this curve guarantees that the output will be a valid probability. It naturally stays between 0% and 100%. It gives us those sensible boundaries that the straight line was completely missing.
All right, theory is great, but let's make this real. Let's use a super classic example. Trying to predict whether a student will pass an exam based on how many hours they studied.
So the setup here is pretty simple. We've got data on 20 different students. For each one, we know two things: how many hours they hit the books, and then what was the final outcome? Did they pass or did they fail? Our mission is to figure out exactly how study time impacts the chances of passing.
And here's just a little snapshot of that data. On the left, hours studied. On the right, the result. 0 means they failed, 1 means they passed. And you can almost see the pattern just by glancing at it, right? Low study hours, lots of zeros. Then as the hours ramp up, the ones start to appear.
So the logistic regression algorithm takes all of this data and it goes to work. But instead of trying to force a clumsy straight line through those zeros and ones, its mission is to find the one perfect S-curve that best describes that relationship. And in doing that, it finds the tipping point, what data scientists call a decision boundary. That spot where you're most likely to flip from a fail to a pass.
And this is what we get out of it. It's brilliant. Once the model has that curve, we can start asking it questions. Like, hey, what about a student who studies for 2 hours? The model says, okay, they have about a 26% probability of passing. They're probably going to fail. But what if they study for 4 hours? Whoa, now the probability jumps all the way up to 87%. It doesn't just give us a yes or no. It gives us a smart, nuanced probability.
Now, this is obviously not just for predicting student test scores. This exact same idea is being used right now in some incredibly high-stakes fields to predict outcomes that literally shape the world around us.
The crucial thing to understand here is just how versatile this is. We're talking about medicine, where it's used to predict a patient's risk of disease. In finance, it helps a bank decide if someone's likely to default on their mortgage. Marketing teams use it to figure out if you're going to buy something. Engineers even use it to predict the probability of a critical system failure. It's everywhere.
Okay, so we've seen how it works, we've seen where it's used. So what's the big idea here? What's the main takeaway from all of this?
It's really this. Logistic regression is a foundational, incredibly powerful way to take messy, complex data and boil it down to a single, simple, meaningful probability for basically any yes or no question you can think of. It gives us a clear framework to make smarter, more data-driven decisions in so many situations.
And that kind of power, well, it leaves us with a pretty deep thought to end on. As our models get better and better at predicting these yes or no outcomes, we have to start thinking about the implications. With great predictive power comes great responsibility. So the question isn't just what we can predict anymore, but maybe what we should. So I'll leave you with this. What's the one yes or no question that you think we should never, ever try to answer with an algorithm? Thanks for tuning in.